Okay, thank you to be here for the lecture of today. Today, as I told you last time, we will consider the design in discrete form of an observer. The name of this observer is Lundberger observer. If next semester you want to attend the class, I don't know if it's next semester, after next semester, I think, on Kalman filter, we will see a special observer, which is the Kalman filter. You attended. Yasin, you attended the class of Kalman filter, not yet. No. It's not this semester, but the next one, not the upcoming semester, but the next one, which is a particular form of observer. How many kind of observers we have? Many, a lot of. Why that? Because the observer is in a controlled system, as I told you last time. Last time we have seen just a flesh out about the discrete form of PI, a PI controller or PID, I don't remember. But of course, if you remember in the lecture of automation or dynamical system, I remember I told you about the sliding mode control. I don't have time to told you about the discrete sliding mode control. Anyway, any kind of controller can be realized also in discrete form. The observer is in a controlled system. This means somehow we know what the controller is, not only for this course, but also for the courses which you attended by me at least. And then we will be easy now to introduce the observer. First of all, what is an observer is? An observer is in a structure, in general, discrete or the continuous, is in a software, is an algorithm, is in a structure which allows to, let me say, observe a variable, let me say in a state variable, but could be also a parameter, which we cannot measure directly. But of course, we can observe also a variable and a parameter which we measure. But the question is, if I measure what I have to have another parallel information. Observe means track. Observe means also estimate. Probably with the word estimate, we can understand better what I intend, even though an estimator is an optimal observer. Kalman filter is an optimal observer. In general, an observer track the signal which I cannot measure directly, or I don't want measure directly because probably it's too difficult to be measured. It's too expensive to be measured because the sensor is too expensive, cost. Because to introduce software is easy instead of introducing a sensor, because the sensor is an hardware with typically costs, membranes. Anyway, in sensor is complicated things, physical aspects, typically costs. A software nowadays doesn't cost because we have a microcontroller in any case in the process. And inside this microcontroller or this Raspberry Pi, Arduino, we can flesh out, we can implement an algorithm. An algorithm, at not only the advantage it is cheap, the advantage is that, in particular, if it's an estimator, what we estimate is better what we are measuring. Because the estimator is an optimal track, an optimal observation. In this sense, we reduce noise. In this sense, we reduce the variance of the measurements. If you consider, for instance, the Kalman filter, we have also theorems that we say under particular conditions that what we estimate is better what we are measuring. This means to measure the measurements are not the true. This is a very important concept. Think about a normal filter, which is not an observer. You have a signal which you're measuring, and then you filter these signals. How we have a signal could be better, not necessary. If you filter too much, it could be that you destroy the information. But if you filter in an optimal way, for instance, you reduce the noise. filtering very often is applied, because if you have a signal which is totally noisy, I say, too noisy. Without particular knowledge, I tune a little bit this filter, and I have an output and a signal which is possibly uh, not so noisy. But the question is, how much I have to filter in order to have the real information? We don't speak about the reality because we don't know what the reality is. No, God knows. Basically, we don't have data. We have just the interpretation of the data. Or better to say, we have data and we don't have the reality. We have just an interpretation of the reality. Basically, we don't exist here at this moment. We exist because we interpret it. We think to be here. It's a little bit now extreme, this concept, but the reality is something which we don't know. This means we have just to interpret. Now, again, if you filter too much, you destroy the information. If you filter too less, you have a noise. You can think that inside you have an optimal way to filter. This is we say estimators, which is in the form of observer and optimized observer. Today, in this course, I have just time to told you about observer without thinking on the optimality. But at the end of this lecture today, I think we can continue in the afternoon. I have time a little bit, but later. We will see that also with this structure here, with this observer, which is not at the beginning an optimal observer, it's not an estimator, including the PSO, I don't know if you remember, particle swarm optimization method, we can realize an optimal observer, for instance, but just an idea. I mean, an observer to be an estimator need to be optimized. And about the optimization in this course, we have seen this PSO. I introduced the PSO at the beginning. The idea was different, but some students from economics told me that they want to do that because they heard that this is a good program in order to be applied in different context. Nevertheless, is okay in this course because in a discrete algorithm. Okay, let me share now the slide. So we will start, what I'm doing. We will start with a concrete example. I hope that I have also the slide, the Simulink. I think so. You have to look at them. Let me see. Okay, here. Let me, I know. Yeah. Look at this example here. You have two equations. This example is in a motor. Oh, excuse me. You are right. Um, you are right. How I can do that? Better? Very good. Stop me because also for the ledge. Yeah, we have two equations. It's in a motor. You can see that we are working with this motor also in different contexts. This is the PhD program of Felix. Of course, this motor here is just a part of a system in order to understand what we are doing. In order to understand what I am telling you is something really that is important for us. Let me see if I have the paper. I don't have here. It does not matter. But believe me, it's a part of a system which we are considering as a possible part of a PhD program of Felix. Anyway, these two equations represent the dynamics of a motor in a DC drive, in which we can see that the first equation, probably I already told you about this, but in any case, represents the electrical part of a motor. Basically, look, if you then consider excuse me, if you, no, uh, again, these two equations are or represent the dynamics of a motor, DC drive. And basically, the first equation is the electrical, let me say, is the electrical behavior of the system, even though we have a feedback from the mechanical one, because omega represented the angular velocity, I represent the current. We have two states, therefore two differential equations. Do you remember about the states? I told you the states are variable which uh, reflect the energy. We have two kinds of energy in the model, or at least in this model. The electromagnetic energy, because of the coils, and the kinetic energy. And the kinetic energy is reflected by omega, the velocity. If you don't consider this, let me say, connection, we have just an RL circuit. But of course, the motor is more complicated than an RL circuit because we have an interaction between mechanical and electrical system. This is the interaction or the feedback between mechanical and electrical system. Anyway, this is the, let me say, the electromechanical equation. And this here is the mechanical electrical equation, because we can see how the dynamics of the mechanical works, mechanical part. But of course, let me say the input. Let me close the mailbox, otherwise we are disturbed. The second equation is characterized by, if you don't consider this, by the mechanical dynamics, in which we can see that J represent the inertia, the derivative of the angular velocity is the angular acceleration. Here we have the friction, which is modeled in a very easy way, because I would like just to introduce the linear observer. The both equations are linear. Of course, if the model is nonlinear, the observer is more complicated. Is more complicated. Let me go ahead just with this example, and then in the project, we can consider also nonlinear observer. About the nonlinear systems, I don't have time to tell you in this course, but if you remember, I told you in the course of dynamical systems, I told you in the course of automation, or we can consider the linearization. I don't know if you remember, I told you about the linearization and automation course, but in any case, we can go in depth through the project. Let me go ahead with this linear observer. The name is Lumberger observer. If I use forward Euler, as almost always, to realize the discretization of the system here, before doing the discretization, I will transform this information here into matrices information. This I told you many times. Row multiply column plus this, multiply this, row multiply column plus 0 multiply this. Believe me, this language here, or that this expression here, is exactly this. I told you many times, I think, in this sense. Clear, no? Row multiply column plus 1 divided L multiply U input. This is equal row multiply column plus 0 multiply U input. Anyway, we represent exactly these two equations. Why this form is suitable? Is suitable, I would like to say it's an advantage because at least when we are working in linear system, we can use the algebra of the matrices, but not only the microcontroller can work very well with tables. Tables are matrix, table is vector. It's really suitable, not only suitable, and big advantage for the, let me say, for the microcontroller. Of course, if you have here some nonlinearity, uh, this representation at some limits, or at least we cannot use directly the algebra of the matrices. About the nonlinear controller, which we didn't see last time, about the nonlinear observer, we can go in depth using eventually some, or through some projects if you want. Anyway, here, do you remember the idea here, assuming that I want to have in output the current. In our case, the output is the measurement output. Of course, I can measure also omega, the velocity. This means the matrix is 0, 1 in this case. But assuming that I measure the current, I want to estimate omega. Of course, I can estimate also current. Even though I measure, as I told you before, to estimate in particular, better to say to observe, but in particular to estimate, estimation is an optimal observation, the estimated current is better if the estimated, again, is optimal as should be, better than the measurements. Or we hope. Okay, do you remember this possible representation now, no? Through matrix A, B, C, D. Of course, if the system is nonlinear, this representation is not exactly valid. At least we don't have properly matrix, which properly means in the matrix we have a constant, no? If we speak about matrix. If in the matrix we have a functions, of course we cannot speak about a linear system. It could be that, as I told you last time, if we have some elements depending just of the time, we have a time variant system. But of course, if A depends of X, we have no linear system. If A, B, C, D depends not from X and U, but depends on the time, we have nevertheless linear, but time variant. Time variant system basically reflects nevertheless the linearity because they are linear, and we can do similar consideration as a linear system. For non-linear, of course, the situation change a lot, but I told you this in dynamical system and so on. But we can go nevertheless ahead also here in this course, but using the project, through the project. Again, forward Euler, we have seen many times, also last time. Um, Let me see. Let me see. No, excuse me. Yeah, it's the forward Euler. X equal xk minus 1, x of t, no? X of k minus 1, u input of t equals u input of k minus 1. Again, the argument we have also ts, no? Or the t depends of, but I didn't put. I didn't put, as I already told you, because of sake of brevity. Here's excuse me. Here's the, let me throw away. Yes, the approximation or the position for the derivative. Of course, I can consider also backward. No? Remember, we have these two possibilities. But let me forget backward because I already told you a little bit. Let me go ahead with forward, which we have this in general. I told you this a lot. At the end, for forward, excuse me, we have this one. Ts is the sample time. I think this I told a lot. No? Yeah, yeah, that's already, I don't need to comment this equation again because we have seen many times. Look that the system which I want to consider now consists, as always, dynamics. We can see x of k is a function of x of k minus 1 in particular, and also u of k minus 1. Very important, this, which states the dynamics, excuse me, because the present is a function of the past. Here is a static equation with the output. And basically, it's what I am measuring. What I am measuring can be written in this form or can be written in this form. It does not change anything because, let me say, uh, this equation holds for any k, but the time, and then let me say an input, and output is the same. Typically, we use this one. Look this. Now, 1 second. Now, let me apply exactly what I told you until now. X of k is equal lambda I, the identity matrix, plus Ts multiply A. This is the structure of A in continuous form. I apply exactly, if you want, I can write. Yeah, huh? Excuse me, this is identity matrix, not lambda I, identity matrix. Let me show you what I intend a little bit better. Yeah, identity matrix plus Ts multiply A. I told you last time where this identity matrix come from. Come from this. I is an identity matrix. I multiply xk minus 1 is equal to xk minus 1. If the identity matrix is, if I is an identity matrix. This means I can write in this form, starting from this. No, I told you last time. Here I can multiply everything by Ts. I bring this on the other side, but if I remark that I multiply x of k minus y is equal to this one, or vice versa, x k minus 1 is equal I multiply xk minus 1, it's clear this form in particular, this form here, starting from this. Yeah, this means this calculation allows to have a discrete model starting from a continuous one. This is continuous model. This is the structure of a continuous model. This was A. No? This was B. It's Ts multiply A. No? Exactly as I told you. Look at this now. Probably it was already very well commented here, probably. This is better than here. I do just a couple of calculations. From here to here, I did just a couple of calculations. Here we have the model in discrete form. Just a few considerations. As I told you last time, if Ts is too small, this representation of the system is not controllable. Why that? Because we have here 0 or almost 0 or something negligible with respect to 1. Here is 0, here is 0. Here it's 0. This means in the representation in the microcontroller, independently of almost 0, of the input is not controllable or not very well controllable because the action and input does not influence the current. If does not influence the current, and not influence the velocity. No? We can see that they are connected. But not only for this element here. If this is 0 and this is 0, or almost 0, I can put also in a very large U input, independent of how small is this, but the dynamics are not connected. This means if Ts is too small, as I told you also last time, we don't have a very well controllable system. We will see that we will not have also a very well observable system. This means Ts should not be too small. Yeah, let me now introduce the concept of the observer. Look at this, these two equations. The observer is characterized by the model, exactly x hat because we will see is not exactly x. I will tell you in 1 minute, but we will want to have that x hat equal x, which is basically the model, the discrete model, exactly what we have here. AD is I plus Ts multiply A, plus BD, which is this one. You can see here, B is the continuous. If I multiply by Ts, is BD, discrete. Again, AD. A is continuous, as I told you before, but inside the structure here, everything becomes AD. The matrix, the discrete matrix. We have seen also last time when I told you about the model. Basically, the observer consists of the model plus something, in particular LD multiply C, C we know, C represents the map of the sensor. Please pay attention, the map of the sensor means, in our case, could be 1, 0, if I measure the current, could be 0, 1 if I measure omega. If I measure both, is the identity matrix 1, 0, 0, 1. It could be that I measure both. And the people ask me, but if I measure both, why I need an observer? As I told you, the idea is to obtain an optimal observer and estimation in which we can demonstrate that what I am observing or estimating is better what I am measuring. Think about a noisy signal. Because the observer is in a filter. An estimator, which is an optimal observer, is an optimal filter. Is an algorithm. Let me say an algorithm. Please pay attention. I am considering something interesting here because LD we will see is a design matrix or a vector. C, I told you now. Please pay attention. This E of k minus 1 is an extremely important signal which states exactly the controlled part of the observer because E of k minus 1, not A, E of k minus 1 error is the error between, let me say, uh, what I am measuring. We will see a little bit later what I intend from the system. At this moment is this here, but one of them or both, not necessarily one, minus what I am observing. In any case, because of the presence of this x hat, because of the presence of the x hat, we have a controlled system, a system with a feedback. I don't know if this is visible. I can produce a scheme, I don't know if it's here, in order to understand better. Let me see. If I have it here, I don't have to produce anything. I think it is important. I don't have here. Uh, I think it's a little bit faster if I open the structure of the observer, even though it isn't a scheme. It's not doesn't matter. It's continuous discrete. Let me see if I find quickly. So I will be a little bit more precise. And we can understand exactly the concept of the feedback, which state, or which allows to understand better than an observer is in a controlled system. Okay, let me see here. Lecture. Okay, here. Kalman. I'm looking for a scheme to show you. I found it. 1 second. I will share. Okay, found it. Why doesn't it work now? Let me share. Look what I intend with this concept of the feedback. Let me see if I find something better. Yeah, look here. This scheme here, which we have the system to be observed. Here, basically, we have the model, but plus something, which is what I am measuring, as I told you, minus what I am observing, which come back in input. Let me see if I can show you in continuous form, mathematically. Probably here, you can see better here, huh? Even though it's continuous, but does not change the concept. I will multiply the difference between what I am measuring and what I am observing, the corresponding, of course. If I'm measuring the current, I have to compare with the current. If I'm measuring the omega, I have to compare with omega. If I measure both, I have to compare both, but separately, multiply by L, which is design matrix, or matrix if I measure both, or vector if I measure one of them. It come back to the system. Here we have the equations in continuous. Exactly what I am telling you now. Here, if you look at this, we have this element here, which is, I don't know if I share, which is the model basically, but with hat, because we will see that it's not exactly x equal x hat. We will want to do have thanks, we will obtain thanks the matrix L. And then we have the error between what I am measuring and what I am observing. And we can see here the feedback. We can see here the feedback because x hat appear here also. But if you want to see graphically, it's exactly here. This feedback. Basically, x hat is coming back. Now, let you so roughly speaking. Let me go ahead, then we can understand better everything. If you remember, the resulting aerodynamics consists of this structure here. I don't know if here is explained, probably no. No, it is. Not very well, but it is. This aerodynamics, the dynamics between what I am measuring, what I am observing, we can demonstrate, I have here a little bit, that consists the dynamics on this equation here, in which, considering a particular LD, this is free. I didn't fix LD. AD is fixed. Depends of TS, depends of R, depends on L. C is fixed, depends what I measure, but LD is not fixed. I can place the eigenvalues such that, you remember, are inside the unit circle in case of linear system. If it's not linear, you remember in my lecture, you have to consider this Lyapunov concept. But anyway, let me remain in linear. For nonlinear, we can do together. We can do together with the project. This is basically the discrete form of this. This means if I discretize it forward Euler, this expression here, believe me, I will obtain, this expression here. Here it's not expressed where this, let me see. Where exactly this come from. Let me show you in the slide quickly where these dynamics of the error continuous come from. Look, here is the real system. Here is the observer. We can see that we have a hat instead of x, and we have this element here. In any case, we have something different, just considering this introduction here. But really, this hat, let me say, basically depends that I don't know exactly the initial condition. I mean, x of 0 is not necessarily known. This means I will call x hat of 0 equal x0 hat, because the initial condition is not known. In any case, x is not exactly its hat for this unknown, from this unknown initial condition. Also, this element here does not belong to the system. That is what I am observing. This means if I do now the difference between, let me go ahead, the equation of the observer, better to say, if I subtract, as is written here, the equation of the observer from the equation of the system, this means the system minus this one can be written in this form here, assuming this position here. I will obtain this expression. Again, the dynamics of the system minus the dynamic of the observer is exactly this expression here, in which I am considering that BU input I can cancel, assuming that B is totally known. Every parameter is known. This is the limitation of this observer here. This is the limitation. This can be overcome with the Kalman filter or a different observer. You input assuming that I am measuring. This means in this sense I can subtract exactly A, the parameter A, are totally known. I will obtain, excuse me, this expression here. And from this is clear, assuming that, as I told you, the error is what I am measuring minus what I am observing, I will obtain this expression here for the dynamics of the error. We know that the dynamic of the error is asymptotically stable if, and only if, the eigenvalue of the matrix A minus LC of these eigenvalues are with real part negative, which corresponds once I have a discretization. Here is really quickly sketched. If I do the discretization with forward Euler, we can see from here, no? Forward Euler. If you do the calculations, we have this expression here, which, if you remember, is asymptotically stable if the eigenvalues of this expression here is mapped into the unit cycle. I would like to skip this because we already discussed a lot about the asymptotical stability. This must be inside a unit cycle. You remember this? Must be less than 1. Of course, I told you last time, this could be, the eigenvalues could be also complex. You remember last time I mapped a little bit the position of the eigenvalues inside the unit cycle. Remember, I told you about some singular yeah, position and so on. Do you remember this pi divided t or ts? To conclude this, we can write this observer discrete observer in this form here. Basically, the observer consists of two inputs, U and error. One through BD, one through LD. LD is something which I can design. Is something which I can design. Yeah, you remember. It's not an intrinsically stable method. No? Backward, yes, but forward, no. This depends of the S. It must be generated, must be considered that the eigenvalue, when I choose TS, must be considered that the eigenvalues of AD through matrix LD should be inside the unit cycle. Let me, as I already told you, let me see. This I already told you. Uh, last time. I don't need to reconsider this expression here, which came comparing the definition of la. I don't need to reconsider this expression here. I don't know if you remember. It could be that I will hold another lecture today. I would like in the afternoon to simulate this. If I find the simulation, I hope to find quickly. I don't need to clarify again because I told you last time about this exact transformation which came comparing the Laplace and zeta transformation. Of course, it's a little bit complicated, but in this course we don't need because we try to apply. You remember here I told you this in the slide what sigma. This is an LaTeX error. Is omega here is exactly correct. We can see. This map I already told you about this map. I don't want to consider more information about that. We can come back eventually if we need. I would like this 10 minutes before stopping for this section here to consider quickly what we can use LD. As I told you, I need to place the eigenvalues of my observer here inside. Must be inside. Yeah, but the eigenvalues, I don't know if you remember math, you see, you have a 1, 0. It doesn't matter which matrix here. In this case, it's discrete. I have to calculate the eigenvalues using this equation here. I don't know if you remember. But in this case, it's not to calculate lambda. I fix lambda here inside. It's exactly the inverse problem. I will calculate LD because LD is free, but such that the eigenvalues calculated in this form here is inside this region here. If I parameterize LD, L11, L21, why has this form here? We have just one input. This means we have just one column, but the states are two. This means we have two rows. That basically means LD multiply C or the CD, no difference in our case, must be in the matrix 2 times 2. We can see here. LD, which multiply C or the CD, no difference between C and CD. A minus LD multiply C. Here we have identity matrix 2 times 2 because we have two states, multiply lambda. But I can fix lambda. Let me show you. I do some algebraic calculations. I will multiply here LD multiply C. We have a matrix on a vector 2 row, 1 column, which multiply in a vector matrix 1 row, 2 columns. We will have 2 times 2. I don't know if it's from math. From math. This multiply this is a matrix 2 times 2. Then I will add the way subtract this and this. This minus this. I will obtain the, believe me, equals 0. Then I do the determinant. This multiply this minus this multiply this with this long expression. And fixing two values for lambda less than 1. The norm of these two values less than 1, typically also a real value if we don't want oscillation. Believe me, we have seen in the course of dynamical system, we obtain two equations in which lambda 1 and lambda 2 are given. I can fix, remember last time I told you that I can map starting from position, where is? If I find the show you. You remember, starting position here, for instance, if I don't want oscillation, in position in this segment here. You remember, I told you. Or if I want oscillation, I can map using the exact summation, or in our case, better, the forward. I can map my desired dynamic here inside. What I intend, I would be a little bit more clear here. No? For a position S, which I want to obtain, I will obtain the position Z in the discrete using this expression here, as we did last time. To conclude, we have here, and we will see later in the afternoon, using the MATLAB function, that if lambda 1 and lambda 2 is given, fixing S using the forward Euler approximation. About the approximation, it could be that I will tell you in another section during the week or next week, we will see. But in any case, we can start with the projects. No? You see, I can calculate L11, L21. In MATLAB, we will see later, I hope that to find quickly the example. We can calculate LD using again the function place, which we used in the controller. Do you remember last time we used the function place to determine the controller. Last time the controller was the name we call K. We call K. Now it's L, discrete in particular. In which instead of A, last time we had A, we have AD clear but transposed. Instead of B, we have C but transposed. P is the same. I mean, P should be characterized by our both eigenvalue, but in discrete form, inside the unicycle. Yeah, let me tell you a little bit again, and then we will conclude in a few minutes. We go to Mensa about this function place. You remember, last time we have seen this, A minus BK. Place calculated in order to obtain K, do you remember? But why we can use nevertheless place here very quickly? Because the eigenvalue of A minus BK are equal of the eigenvalue of A minus BK transposed. Why that? Because the eigenvalue of the matrix M are equals of the eigenvalue of the matrix M transposed. Math for engineering. It's here. No? We can see exactly what I told you now. But this expression here which is validated by this theorem, no? The eigenvalue of the matrix equals the eigenvalue of its transpose. This expression here can be written here. If you remember, I told you in math for engineering the property of the transposition, but if you don't remember, it's not important. I have to invert, not the product. It's distributive with respect to the algebraic sum, and then I have to invert the product. Now, we can see very well that instead of A, I will have A transposed. Instead of B, I will have C transposed. And this means the result, instead of K, I will have L transposed, because I will transpose everything. Now, of course, this explanation is a little bit rough. We can understand. I mean, I can understand very well, or approximatively well, that instead of A, I have A transpose. Instead of AD, I have AD transpose. Instead of K, I will have another matrix which I called, instead of KD, for instance, which I call now LD transposed. You can understand very well. Instead of this, I have something which I called LD transposed because it's transposed. But why we have a B here, and you have a B transposed, which becomes C? It's a little bit more complicated. I have something in the slide, which I don't want to show you, but I will tell you now. This is related to the duality between the controllability and the observability. The duality is in the concept related to the transposition, but the transposition of the matrix A. But instead of the matrix B, we have the matrix C transposed. Yeah, this means if you have a system characterized by the matrix A, B, C, if the system is observable and controllable, or controllable and observable, we can nevertheless speak about the same concept, observable equals, or controllable equals observability, or controllability equals observability, for two systems. One is AB, and the other is A transposed, C transposed. It's not a demonstration, but we can demonstrate this. Therefore, at the end, I will use in MATLAB, we will see in the afternoon, in the same form as before, but instead of, as last time, to place the matrix, to place eigenvalues, which I have in P for the system characterized by AB, the output is K, I will place eigenvalues in P, in our case in discrete, now in discrete. Last time we have seen the controller, but continuous. But of course, the same thing can be done. No, at the end we will see also discrete, excuse me. At the end we will see also discrete, AD, BD. Yeah, it's basically the same P, if I want the same eigenvalues, but typically, believe me, the observer is much faster than I told you last time, than the system, because I have to use the information of the observer to control. I show you what the intent now. But of course, as I told you very quickly about the duality, A will be A transposed, B will become C transposed, even though this is clear. From my words, it's not really clear what is the duality. Here, a little bit better. At the end, why I need, and we conclude, and then we will reconsider in the afternoon today, why I am considering an observer. Not only because I am curious to know what happens in the system, but very often, look at the scheme here. I don't know if I share, not yet. It's shared. If you look at the scheme here, we can see that very often we need for the controller something which is not possible to measure, or I need for the controller all states, and not all states I measure. I measure all states because it's too expensive, because it's not accessible. The controller very often need a variable which is not possible to be measured, or is not represented in the scheme, but the controller needs to know or to have information about all states. Let me we go to Mensa now because in 20 minutes I have a meeting. We will meet in the afternoon again if you have here to go a little bit more in depth, or during the week, how do you know you prefer. But in any case, I will stop here. What do you prefer? During the week. Okay, this means I will send you an email again. It is better also for me because I'm full for meeting today, and then we will go in depth on this again. I will present the example because I have to look, I need also to look where the example is, otherwise we can build directly. But some aspect I would like to repeat again because it was a little bit too fast. No? But we don't need to go theoretically in depth in this course because the course is not oriented to the theory. In any case, thank you. I will inform you during the week or next week to go in depth on some aspects here. Thank you for attending this lecture.